Yeah. All right, thanks for coming. So today we have met Kwan from ISTA. We talk about permanence, right? Random matrices.
Yes.
Please.
Thank you very much. Yeah. So I changed the title and the subject of the talk at the last minute. So the original thing I was going to talk about, I am still going to talk about in Seoul on Thursday, if any of you feel like making the trip there. But this is more recent. This is very recent work on permanence of random matrices. It's a topic that I've been interested in for quite some time now. I didn't really know how to make progress on anything until, so I'm excited to finally have some progress to share. This is based on a paper that is joint work with these two amazing people, with Zach Hunter, who is a PhD student at ETH Zurich, and with Lisa Sauermann, who is now a professor at the University of Bonn. Okay, so I thought I would start by sort of motivating this whole topic with some introduction to the singularity problem, which is a closely related problem which has seen quite some interest over the years. By the way, I should say that, please interrupt me if I, at any point, you would like to ask questions or anything. I would much rather everything be fully understood than get through whatever notes I have here. But anyway, so the starting point for the singularity problem is a theorem of Komlós. This was from 1967. And basically what he proved is that random discrete matrices are usually not singular. They're usually invertible. One of his theorems, and so you can consider a variety of different types of discrete random matrices. Let's, for this talk, consider just random matrices, n by n random matrices with plus minus one entry. So I flip a coin for each entry. Should it be plus one or should it be minus one? Totally independently. There's 2 to the n squared possible matrices I can get. Each one is equally likely. Okay. And then Komlós' theorem tells me that the probability that it's singular, the probability the determinant is 0, tends to 0 as n tends to infinity. So this is, I mean, it's an influential theorem. It's not terribly surprising that this should be true, because if we think, like in the continuous case, the determinant is some polynomial, the set of matrices where it's 0 is some measure 0 set, so somehow it's not surprising that generically it's not 0. But what maybe is surprising is that this is not that easy to prove. So you need to have some kind of idea. And in fact, this is perhaps the most famous application of something called the Erdős-Liljevalófit theorem about anticoncentration of random sums, which is sort of the key ingredient to prove this. So since this initial work of Komlós, there has been really intensive effort on trying to understand this probability a bit more quantitatively. So not just does it tend to 0, but how fast does it tend to 0. So Komlós' proof does give some bound. It gives a bound of about 1 over square root n. But one of the most important breakthroughs in this area was some subsequent work, I think about 30 years after this original theorem of Komlós, by Kahn, Komlós and Szemerédi. Kahn, Komlós, and I suppose this should have maybe, and Szemerédi. We proved an exponential bound on the singularity probability. They proved that the probability that the determinant of a random matrix is 0 is at most, let's say, exp of minus 0.01 times n. And so, since this, the effort has gone into trying to understand what is the right exponent. So we know that the probability is exponentially small. And maybe let me not write every single thing that has been proved, but let me just sort of say out loud that this probability was improved to, I think, 3/2 to the power of n by Tao and Vu in some influential work where they found some connections to additive combinatorics, additive number theory. Then this was refined further by Bourgain, Vu, and Wood, who improved it to 1 over square root 2 to the power of n. And then there was this totally different geometric method introduced by Rudolfson and Verschinen, which also can be used to get exponential bounds. And using this geometric approach, together with some ingenious technique called inversion of randomness, the most recent result, the state of the art, was proved by Tikhomirov, who proved the correct base of the exponent. So the probability of the determinant is equal to 0 is at most 1/2 plus little o of 1 to the power. And this is the correct base of the exponent. This is essentially best possible, I mean up to this little o of 1, because one way that a random matrix can be singular is if two of the rows are exactly the same. And well, if there's two choices for each element, then the probability that two rows are the same is up to lower order terms 2 to the minus n. So this is up to lower terms the answer for what is how likely this is. How likely is a random matrix to be singular? Yeah. So all of these proofs, all of the intermediate results, some of which I wrote, some of which I didn't, all sorts of really interesting stuff goes into these proofs, and I'm not going to really say too much in detail about that. But let me just sort of tell you at least the starting point for all of this work. Let me say proof idea, which is really like step 0 of all the proofs. You're going to use the observation or some variant of the observation that, I mean, I'm not sure I can even call this a proof idea, but really the first thing is that for a random matrix to be singular, so for the determinant to be 0, that's the same thing as the event that there exists a non-zero kernel vector. So there exists some v which is not equal to 0, such that an times v is equal to the 0 vector. This is 0 vector. Okay. Of course, this is a trivial linear algebra observation, but it's useful for these types of problems because this type of event, the probability that at least if I fix a vector v and I ask what is the probability that that is a kernel vector, well, okay, so my matrix has independent rows. I mean, all of its entries are independent, which means that the entries of v are independent, and each of the entries of v is a sum of independent random variables. So it's something that you can try to get a handle on, and in particular, the Aristotle-Laffer theorem is a way to get a handle on things like this. Of course, the real work in all this stuff is to really understand what are the combinatorial features of a vector v that control how likely it is to be a kernel vector, and how do the different sort of possible kernel vectors correlate with each other. And that's where most of the work goes. Yeah, but the reason I don't want to say more about this is because this talk is really about a different problem, a closely related problem where none of those techniques work at all. So specifically today I want to talk about the permanent. Let me just remind you what this is. So the permanent is like defined in a very similar way to the determinant, but it's much less friendly in various ways. So the permanent of a matrix, let's write an, or let's just write a, is the sum over all permutations of the product over all I of the a I sigma I. So the entry in the ith row in the sigma ith column. So it's the same definition as the determinant, but I haven't put the -1 signs in there. Yeah. So this notion is, I mean, it's in some ways it's kind of weird because those -1s sort of have a purpose. They make it mean stuff about linear independence and so forth. But this is an important function. I mean, in combinatorics, it's like if you interpret a matrix in terms of a bipartite graph, then it's like counting perfect matchings with an appropriate weighting. In computer science, it's sort of a fundamental example of a function that is difficult to compute, and that's a lot of the interest there. And many things can be reduced to computing the permanent. In particular, permanents of random matrices. There's various reasons why to care about them in computer science. There's some surprising connection to quantum computing somehow, that quantum computers can somehow compute permanents, and so there are some conjectures along these lines. So as I said, the thing about permanents is that unlike determinants, they don't really mean something. So the determinants mean something about linear independence, and I mean the determinant is the volume of some parallelepiped. There is nothing like that, and in particular there is nothing like this. So the permanent being equal to something doesn't tell you anything about linear independence. And so presumably, well, one can imagine that this kind of stuff should still work for permanence. The kinds of theorems that are proved for determinants should still work for permanence. But all the proofs are going to immediately fall apart because even this sort of first basic observation has no analog for permanence. Somehow the permanent is like just a polynomial, and proving things about it, you really just need to think about the terms of this polynomial and how they interact with each other. Okay. So there is one thing that is known about permanence of random matrices. It's a theorem of Tao and Vu. So theorem of Tao and Vu. They managed to prove the permanent analog of Komlós's theorem. So they managed to prove that the probability that the permanent is, let's say, 0, but really the probability that it's anything is at most, well, they proved n to the minus 0.1. Okay, so it is something that tends to 0 as n tends to infinity. They didn't really try to optimize this 0.1, but they observed that their method was not capable of doing anything better than 1 over square root n. And the reason is that this theorem uses the Aristotle-Wood-Offord theorem in roughly the same way that Komlós's original proof does. And so, well, I haven't told you what the Aristotle-Wood-Offord theorem is yet. That'll come in a moment. But that theorem has a 1 over square root n in it, and that's the bottleneck for this stuff. So it's not hard to check. Well, with maybe some additional tricks, one can in fact prove a bound of roughly like n to the minus a half plus little o plus little o of 1. But to go beyond this, there are sort of more sophisticated variants of the Wood-Offord theorem that were very effectively applied to this subsequent work, but don't seem to work here. Okay, so I thought I should say just a little bit about how Tao and Vu proved this, because they did not use any kind of linear algebra. Their approach was kind of dynamical. So thinking about the permanent as the result of some kind of random process, some kind of evolutionary process even. So let me tell you how that goes. In fact, maybe I'll be efficient with board space. Let me start here. So how did they prove this? Well, the first observation, which is not really their observation, it's a basic observation, is that just like the determinant has a minor expansion formula, so does the permanent. So the first step is to observe that the permanent of a matrix is the sum over all I of the entry in the last row in the ith column times a permanent of a submatrix, which I'll write A n brackets I, where A n brackets I is obtained from A n by deleting the last row and ith column. So really exactly the same thing as the determinant holds for exactly the same reason, except that you don't put minus signs in there because there's no minus signs in the permanent compared to the determinant. So what this is telling you is that if I want to know the permanent of my matrix, it suffices to know the subpermanents, the n minus 1 by n minus 1 subpermanents in the first n minus 1 rows, and then I can add them with these weights. But of course, those subpermanents can themselves be expressed in terms of subpermanents in the first n minus 2 rows, and those can be expressed and so on and so forth. So you can imagine that I reveal my random matrix row by row, at each step exposing new subpermanents, and trying to understand some kind of process of like how the permanents that I've revealed so far decide the new subpermanents in the next row. So step 2, which is really where all the work is, was to reveal the matrix row by row and consider how the subpermanents sort of evolve. Yeah. And they really did use this sort of metaphor of evolution because in some sense, like, a k by k subpermanent is determined by the k minus 1 by k minus 1 subpermanent sort of above it. So there is some sense in which every permanent has like parents from the previous step, And if you've got parents with large permanent, you're more likely to have large permanent, and there's some way to shrink this. So this step is difficult because, so this random process, this sort of evolutionary process, there's a huge amount of dependence in it, because to go from if you recursively break it up in this way, you'll see exponentially many different terms arise during the process. For example, you'll be forced to consider all the n over 2 by n over 2 subpermanents after revealing n over 2 rows, and there's there's exponentially many subsets that look like that. And so everything intersects really a lot. And so the real ideas of Tao and Vu were some way to isolate some subset of evolutionary lines that go through this random process in such a way that you have enough independence just from this information in such a way that you can make worst case assumptions about everything else and it'll still work. So it's completely elementary. Somehow the only thing you can do for the permanent is completely elementary because it has no geometrical algebraic interpretation, but it's really very ingenious. So so the new thing that I would like to tell you about today is that we finally have a sort of new approach to study permanence of random matrices, and we managed to finally improve on this polynomial type bound and prove an exponential type bound, so a permanent analog of the Kahn, Komlós, Szemerédi theorem. So we proved, this is with Zakanta, myself, and Lisa Sauermann. We proved that the probability that the permanent random matrix is equal to, and let me write it in a bit more general way than 0, the probability it's equal to anything is at most exponentially small. Let's write 0.01 there for all x. And the reason I write it for general x and not just for x equals 0 is not because it's necessarily that interesting. The same proofs work for everything. But because a trivial consequence of the fact that the probabilities are exponentially small is that the support must have exponential size. So this implies that there must be exponentially many different permanents you can attain by plus minus 1 matrices. And in fact, even that sort of simple sounding thing was open until now. So until this year actually, the best bound on the number of permanents of plus minus 1 matrices, which are n by n, was n. So the best bound we had was linear. This year was improved by Ingram and Razborov to a super polynomial bound using some quite different methods, but this gives an exponential bound.
Does the problem change if you make 0-1 matrices, for instance?
Yeah, so for this determinant stuff, not really. So everything, it works exactly the same with 0-1 matrices. For the permanent, one could actually predict that you might get, it might depend on whether 0 is in the support of your entry distribution. So the reason that you can't do better than a half to the power of m for the determinant is that if you have a pair of equal rows, then it will be 0. There's nothing like that for the permanent. But it is true that if you have a row which is all 0, then the permanent will be 0. So that is a local reason. So once you have a local reason, you expect exponential behavior. And so it could be that the bound is quite different in the plus minus 1 case and the 0 case for this reason. I'll say a little bit more about that and some of the problems at the end. But I should say that this result is insensitive to the distribution of the entries. So in particular, it holds for the 0-1 case. It holds for, if you fix your favorite distribution, generate a random matrix with that distribution and send n to infinity, you get the same. Well, the 0.01 will change, but otherwise it'll be the same. So one might imagine that in the 0-1 case, because permanents count things, and if you put minus 1s, then it's like counting with cancellations. You might imagine that things should be significantly easier in the 0-1 case. I don't necessarily see, so I don't see an easier way to prove our theorem than the proof that I'm going to give you today. Any other questions? Yeah.
Do you have any results saying that these are significantly different somehow? The problem for the permanent and for the determinant? Because in some sense, if you place plus minus 1s randomly, then maybe you would say, well, this minus ones that you have in the definition of the determinant actually sort of cancel out by randomness, and that like
yeah.
I don't know. Like
So there's various things that are conjecturally true. So I don't know how much detail I want to go into now, but so in particular, so our proof also works for the determinant, and I don't know any way to really prove things about the permanent that doesn't accidentally also prove them for the determinant. Somehow you can think of the permanent as being like, studying the permanent is like studying the determinant, but you're only allowed to do combinatorics somehow. So some things that are sort of true for algebraic reasons, like this issue that having two rows equal implies zero determinant, you don't have this, and so it could be the fact that the truth is that it's probably super exponentially small, but that's not true for the determinant. So there could be some separation like that. I think the general opinion is that probably the determinant, apart from local issues like the likelihood of hitting zero, the distribution should be basically the same. In particular, there's a conjecture that the permanent has a log normal distribution. That the log of the permanent is asymptotically normal, which would match what is known for the determinant. But we don't know how to prove that because there's no interpretation of the permanent. So that's.
Could be the same. Like
Well, not exactly the same.
the distribution.
The asymptotic distribution could be the same. Yeah. Yeah. So there's also some classical stuff. Like Polya had this question about whether you can represent the determinants. You can represent the permanent using determinants, and the answer to that seems to be no. So I don't think there's like on a direct algebraic level there's a connection, but statistically I think yeah. That's way more detailed than I wanted to go into, and let's hope I can. Anyway, okay. Yeah. So that's our theorem. It also works for the determinant. So let's talk about how to prove this theorem. Any more questions before I do that? Okay. Yeah. So my plan is to the proof of this is actually short. So this is a proof that works simultaneously for the permanent determinant, but it's not necessarily more complicated than the Kahn, Komlós, Szemerédi proof, which only works for the determinant. Still, there's a limit to what I can do in a 1-hour seminar. So my plan is to sort of give you a version of the proof that is overlooking some key difficulties. Hope you don't notice, and then at the end we'll talk about how I cheated you, so to speak. Okay, so the first ingredient we will need is an anticoncentration theorem, so something like the Erdős-Lobodov theorem. So finally we'll talk about what that is. So let's introduce some notation for that. So let's define Q of a random vector x to be the supremum over all little x of the probability that my random variable is equal to x. So I'm going to call this the anticoncentration of my random variable. It's just how likely is it to hit some value. So if this is 1, then it's a constant random variable. It doesn't have any randomness. If it's small, then it's anticoncentrated. That's my notation. And we will be using a theorem of Keston, which is a beautiful theorem, and I think deserves to be better known than it is. I think it's very few people know about this. It's got almost no citations, but it's a very nice theorem. It says that if y1 through yh, well, a special case of Keston's theorem is that if these are independent with each of these random variables needs to have bounded anticoncentration. So let's say it's at most p, and let's assume this is at most a half to prevent things from getting too trivial. Then the anticoncentration of the sum, sorry, it was y, not x, y1 plus yh is at most a constant times p over square root h. So in other words, if you take a sequence of independent random variables, they each have a certain level of anticoncentration, and then you add them all up, you boost the anticoncentration by a factor of square root h, where h is the number of terms in the sum. Okay. So So now I can say, so the Aristotle-Wood-Offer theorem that I've been talking about several times now, it's basically the case of this when p is equal to a half. So it says that if you take a bunch of, usually it's stated as plus minus 1 coin flips, so they each have anticoncentration a half. If you add them up, then you get anticoncentration of most 1 over the square root n. This is a vast generalization of that, where I make no assumption at all about p. Like p could be exponentially small compared to h, and still I get some boost. So this is saying that if you add together independent random variables, you get a boost to the anticoncentration. Now I don't want to prove this for you today, but I promise the proof of this is quite short and very elementary. So I encourage you to read Keston's paper if you're interested.
So
yeah.
is there extensions of this instead of putting linear functions inside the bracket, some other polynomial?
So I would really love to have a theorem like that because it would allow me to. So at the end I'll say one thing that we don't yet know how to do is to handle symmetric random matrices. And symmetric random matrices correspond to quadratic anticoncentration theorems. And we don't yet have a good analog for that. Yeah. So Keston's theorem is completely combinatorial. The proof, it's very similar to the proof of the Aristotle-Wood-Offer theorem, if you know what that is. It's some combinatorial argument that uses, in some clever way, that the reals are linearly ordered. If you do that proof and you include some interesting recursive step, then you can prove Keston's theorem. That's what he did. Okay, and so we are going to use this via a corollary of it. So maybe let's see if I can. So there's another board behind here.
Yeah, you can move everything one like this.
What's the best way to do this? Well, you've just lost Keston's theorem.
That's right.
So I want to use it via its following corollary. It says the following. If I let x1 through xn now, oops, xn. So I realize n looks similar to h, but let's try and distinguish them. Be independent. And let's assume that each of these random variables have anticoncentration at most a half. And then let I be a random subset of the integers from 1 through n with size n over h. And let y subscript capital I be the sum over all the indices in capital I of xi. Then q of the sum x1 plus xn is at most, and I want to write something else, so let me leave a space. So this is at most a constant times q of yi over square root h. Okay, so let's interpret what I've just written. So I have a sequence of random variables, and I'm going to sum them up. I'm going to sum them all up and investigate the anticoncentration of that. But I'm also going to consider like a randomly subsampled version of the sum, like a randomly thinned out version where I don't add everything. So I don't add all the n indices together, but I just add the ones in a random subset of size n over h. So this is the anticoncentration of the sort of thinned out version. And I'm claiming here that the anticoncentration of the entire sum is better than the anticoncentration of the thinned out version by a factor of square root. Okay, and the thing that I want to put in the middle here is that, so this, I can sandwich between these two things, big O of the probability, I don't think I've left myself enough space, of the probability that yi star is equal to 0 over square root h, where yi star is equal to the sum over all I in the set I of xi minus xi primed for independent copies xi primed of xi. Okay, so this is just like y capital I, except that I've sort of symmetrized the distribution. So instead of considering just the sum of the xi's, I'm considering xi's minus an independent copy of themselves. And the reason that I'm doing that is because this probability that yi star is equal to 0, this probability, this is just the anti-concentration of yi star. So it's an easy consequence of the Cauchy-Schwarz inequality that if you symmetrize a random variable in this way, if you take any random variable and you subtract an independent copy of itself, the most likely value that that thing takes is 0. So it's more likely to take that value than any other value. And it's just convenient to not have to, like I'm going to be doing averaging arguments soon. And averaging Q is a bit funny because I'm averaging a supremum of probabilities. It's much more convenient to average actual probabilities. So that's the reason I want that. But you should think of, morally speaking, this is the key thing, and this is some technical version of this thing. And this inequality is supposed to be trivial. So it's just a fact that if you have any two random variables and you add them together, the anti-concentration is better, or at least not worse than each of them individually. Okay. 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 So why is this a corollary of Keston's theorem? Now I have another board. This is going to be very nonlinear. So let me say proof idea. So the reason that this thing is in fact a corollary of Keston's theorem is that I can, instead of considering a random subset I can instead consider a random partition. So I can randomly partition n as I1 union through IH, where the size of each thing is exactly n over h. So then the sum of x1 through xn is of course equal to the sum of y I1 plus dot plus y IH. So I've just regrouped the variables here. So adding up all the random variables is the same as dividing them into buckets and adding the bucket of each thing. Now you can sort of see how I might apply Keston's theorem, because the marginal distribution of each of these y's, I mean, each of these I sets is just a uniformly random set of size n over h, and so this, I mean, each of these has a distribution yi. Now, it's not quite so obvious how to apply Keston's theorem to this setting, because these yi's are actually not independent, because this was a random partition. I mean, they're conditioned to be disjoint, so they're not independent. But if you sort of, if you first condition on this random partition, then apply Keston's theorem, and then take the resulting thing and average it over choices of the partition, then that works. Let me not write the details of that, but let me also mention the way that this yi star comes into things is the following observation, which is good to know in general. The probability that for any independent random variable z1 and z2, the probability that the sum of them is equal to something is always, at most, by the Cauchy-Schwarz inequality, at most the probability that z1 minus an independent copy of itself is equal to 0 to the power of a half times the probability that z2 minus an independent copy of itself is equal to 0. And that's by Cauchy-Schwarz. So this is literally just if you take the formula for this by convolution or whatever, you get some sum, you apply Cauchy-Schwarz to it, you get this. But that allows you to compare sums of independent random variables with sort of symmetrized versions of themselves. So that's how you bring y star into the picture. Okay. So let me maybe leave it at that for why Keston's theorem implies this corollary. And then let's talk about how we use this corollary. What are we, how are we proving anti-concentration of the permanent? Yeah, so maybe let me erase. This slide. Yeah, so I should say this this corollary is I think, very nice and probably useful for other things. It's not, I wouldn't necessarily sort of sell it as like the main new thing that we're doing, because quite similar sort of comparison-based inequalities have been used previously by Kahn, Komlós and Szemerédi in the study of the singularity problem. Some Fourier analytic methods have been used in that setting. But this is nice. I think it's quite transparent. And what is really new is the way that we're going to apply this inequality. So yeah, so the way I want to apply this this inequality is I want to say, so we know from is the Tao Vu, no, the Tao Vu thing is not here anymore. So the Tao Vu, we know from the Tao Vu approach that we've got a minor expansion formula for the permanent. I can express the permanent as a random sum. So I want to apply this corollary of Keston's theorem to the minor expansion formula to tell me that the permanent is more anticoncentrated than a randomly thinned out version of the permanent in some setting. So that'll show me the permanent is more anticoncentrated than something else. And then I want to say that thing is more anticoncentrated than something else, and that thing is more anticoncentrated than something else, and I'll keep thinning it out sort of in different ways, and eventually I'll have such a good bound that it'll be exponential. That's the plan. So let's do that. So let's proof of main theorem. Okay. So so first let's an prime be obtained from an by deleting the last row. So what we're interested in is the anticoncentration of the permanent. I mean, our objective is to show that this is exponentially small. I'm going to consider the anticoncentration in the conditional probability space where I condition on the first n-1 rows. Okay. And so we know by the minor expansion formula, well, the permanent is just the sum over all I of a and I times the permanent of a and brackets I. But the point is that if I condition on the first n-1 rows, this part isn't random anymore. So this is just a uniformly random weighted sum. So it's a sum of independent random variables, where the only randomness is now the elements in the last row. So by Keston's theorem, this is at most Q of sum over all I of A and I minus an independent copy of A and I times the permanent of A and brackets I. Sorry, I should write the problem that this is equal to 0. Given where this is an independent copy of this. So I'm really just applying this corollary of Keston's theorem. This whole thing here is my yi star. So this is a random subset of n over h indices. So I'm taking a random subset of n over h indices. I'm only summing over what happens within those indices. And within those indices, I symmetrize the random variable by subtracting an independent copy of itself. So this is what Keston's theorem tells me. But then I apply the minor expansion formula again to observe that this whole sum can be interpreted as a permanent of something. This is equal to the probability that the permanent of A star is equal to 0, where A star is obtained. Sorry, this is given from an by randomly thinning out the last row. And symmetrizing the last row. Yeah, so namely, this quantity here is the permanent of the random matrix, where in the last row, I delete everything outside of that special random subset of size n over h, and within that random subset, I symmetrize. Okay. So then if I take this whole thing, I take this whole business and I average this over outcomes of the first n minus 1 rows, I have proved that my board management is really not. I'll put this up here.
So Matt, is there a square root size of I missing, or I'm not understanding something?
Oh, sorry. Yes, I'm missing the whole point here. This it's this times
N over I.
1 over the square root of h. The whole point was that I get a boost in the probability. Yeah. So this is equal. Right. So Keston's theorem tells me that this is more anticoncentrated by a factor of square root h than a random within that version of itself. This is the same as this. This is just a reinterpretation of this, and that's what's happening. Are we all on the same page?
Wait, so this time is h and n the same thing?
No.
No. Wait.
So
H is N over I, right?
So h is, we don't yet know what h is, but this is true for any h. So I'll choose h in a
okay.
second. So yeah, I will choose h to satisfy certain inequalities in a moment. Yeah, so h, yeah, it's going to be a large constant in the end. So I'm going to thin things out just by, in the end, I'm going to thin things out just by a large constant factor. Okay, so if I average over a n primed, I get that the anticoncentration of the permanent of an is at most the probability that the permanent of a star is equal to 0, and which is certainly, so the anticoncentration is a supremum over probabilities like this, so this is certainly at most this. Okay. So what I've really just shown is that the permanent, and again I'm forgetting some square root h factors. What a mess. Okay, this is at most. Okay, so the permanent is by a factor of square root h more anticoncentrated than this, the permanent of this other random matrix A star. Yeah, is at most the probability of 0, which is at most the anticoncentration. Okay, so now what I have shown is that the permanent of my desired random matrix is more anticoncentrated than the permanent of this other random matrix. Okay, and this is the point where I needed this star nonsense with this yi star, because like the law of total probability tells me that if I average this probability, if I average this conditional probability over outcomes of A n star, that's just the unconditional probability. You can't quite average conditional anticoncentration in the same way, because this is a supremum of probabilities. The inequality only goes in one direction. So yeah, so I've in this inequality here, I've used the good direction of averaging here and the law of total probability there. Okay. Are we happy with this? Okay, so, right, so this seems promising because A star is basically the same random matrix that I started with, but I've done something special to the first row. You might imagine that then I can do the same thing to the second row to show that A star is more anticoncentrated than A star star, or A star star is doing the same thing in the second row, and so forth, so on and so forth, until in the end it's I get some good bound. That's basically what's going to happen. Let's see how to implement that. So. Let's let f of n be the supremum of q of the permanent of b over all random matrices B, so all possible distributions on matrices with, which have n random plus minus 1 rows and some number, possibly 0, other rows. And I'm not demanding anything at all from these other rows except that they contain some non-zero t by t subpermanent. Oops. Okay. So the point is that the permanent, so the anti-concentration of the permanent of an, that's supposed to trivially be at most f of n. And the anti-concentration of A star, that's supposed to be like that's supposed to be at most f of n minus 1. Because it's got n minus 1 random rows in addition to this special row that I've randomly specified, and who knows what the distribution of that is. So I'm supposed to have, in this definition, in f of n, I have n random rows which are uniformly random plus minus 1, and then possibly some other junk on top. And the only thing that I'm requiring from the other junk is that it doesn't make the permanent 0. So of course if you put a 0 row, then you get nothing interesting, but that's all I require. So then let's
So the B is, how big is the matrix? N plus T rows?
it's n plus t by n plus t. I'm
N plus T by
only
N
working
plus
with square, yeah, I should have written that. But, I'm only ever working with square matrices. It only makes sense to look at well, for now it only makes sense to look at the permanent of square matrices. Okay, so then, with this definition, the anti-concentration of the permanent of A star, I want to say that it's at most f of n minus 1 because it's got n minus 1 random rows. But I have to worry about this degeneracy condition that these bonus rows are not allowed to all be 0. So this, what I can say is that the conditional anti-concentration of A star, given the last row, is at most f of n minus 1 if the last row of A star is non-zero. Okay? Because this is the special row that I did the random thinning out to. Yeah, if I condition on what happened there, the rest of the matrix is still uniformly random plus minus 1s, and I only needed to have a non-zero 1 by 1 subpermanent, which is the same as being not all 0. Okay. Now, what is the probability that the last row of A star is non-zero? So this happens, with probability 1 minus 2 to the minus n over h. Okay. So why is this? Because this last row, which has been randomly specified, it's only non-zero on a set of size. It only can be non-zero on a set of size n over h. And when I did this symmetrization, like I take the difference of two independent plus minus 1 random variables, that can be 0 with probability of half. So the probability that I don't get 0 is this. Okay. Okay. And so now I can do the same, exactly the same stuff that we saw here to show that the permanent of AN is more anticoncentrated than the permanent of A star. That same argument shows that f of n is at most a constant times 1 over square root h times f of n minus 1, except for a possible error term of 2 to the minus n over h. Okay. So in general, you can do the same argument. You have to worry about the possibility that this additional specified row is all 0, or only contributes 0 subpermanents, and that is exponentially small. But then, other than that, you get a boost over what you got in the last round. So there's some recursive estimate, and it's not hard to show by induction that, well, if you iterate this for this thing, you have to choose h to be a large constant. So I want this boost to be meaningful. So I want this square root h to overpower the constant in the big O notation. I can't let it be too large, or this thing will start to be sub-exponential, like sub-exponentially small. But if h is a large constant, then I'm going to get, by induction, some exponential bound here. Okay. So that's sort of the approach of the proof. Any questions? Yeah. So the way that this, the way that I've cheated you here, is that, well, now it's gone, so you probably can't even remember. But Keston's theorem had an assumption. The assumption was that each of the individual random variables in the sum has some anti-concentration. Like I said, it's almost a half. And you need some assumption like this, because if I take a bunch of random variables that are not random at all, they're just constants, no matter how many of them I sum up, I'm not going to improve any anti-concentration. It's always going to be 1. So you somehow need to get the anti-concentration off the ground before you can start boosting it. And the concern could be that where are we? In here, when I try to apply Keston's theorem here, it could be that all these subpermanents are 0. And then, I mean, this whole thing is just a sum of zeros, and there's nothing to boost here. So I really need an additional error term here that corresponds to the possibility that I have tons of 0 subpermanents in the first n minus 1 rows. Okay, because in that case I won't be able to apply Keston's theorem. So how do I control that error term? How do I control the probability that I get lots of 0 subpermanents in the first n-1 rows? Well, I just do the whole thing all over again. So those n-1 by n-1 subpermanents, they're still permanents of random matrices. I can do exactly the same proof to understand their probability. That's going to involve n-2 by n-2 subpermanents, so I do exactly the same thing there, and I just keep iterating this, and I get lots and lots more terms. But you can check that it doesn't affect the asymptotics of... it's a little bit delicate, but you're going to get some geometric sum of different f's. So you need to consider... So really f of n is at most f of n minus 1 times some coefficient times f of n minus 2 times some coefficient times f of n minus 3, and if you do everything in the right way, it's all geometric and it all works. And that's really the proof approach. That's how this whole thing works. Yeah. So let me end with some open problems. How am I doing for time?
Everything good.
When did I start? I started at...
Oh,
yeah.
50 minutes after 9.
Okay, good. Yeah, so I've already talked a little bit about some directions, but let's reiterate some of them. Let's say some more. That sticks. Good. So one shortcoming of this stuff is that for the determinant, we now have not just an exponential bound, but the right exponent. We have roughly 2 to the minus n. And unfortunately, it seems that our approach cannot do this. So somehow it feels like there's some 2's coming out of this approach. So it sort of feels like maybe there's some twist of this approach that could get the right bound. But I don't know how to do that. So let's say the conjecture is that the probability of the determinant of a 0 is almost, what's the little one? I think this would be really interesting because it would be necessarily, well, unless you found some magic that's true for the permanent and not true for the determinant, this would probably be a totally new proof, a totally new combinatorial proof of Komlós theorem. That sort of, somehow you're not allowed to use anything except combinatorics because it's permanent. And as we briefly discussed earlier, one can also conjecture, so this is a conjecture of Van Vu, that in fact this this thing is super exponentially small. So that this would be, if this were true, as we've discussed, this would be a distribution-dependent fact. So everything I told you, all that stuff works for arbitrary entry distributions. This would only work for plus minus 1, or at least it wouldn't work for 0, 1, because you have a possibility of a 0 row. But this is what I think would be really interesting, because you would have to find some way to specifically use a distribution of plus minus 1. And again, this seems sort of like something the proof can do, because really the reason, I would love to take h to be huge, so that I get some huge boost to this probability here. But the reason I can't is this error term that corresponds to the fact that the row could be all 0. So somehow, in some way, you're seeing the meaning of all 0 rows. But unfortunately, even if you start with the plus minus 1 distribution and you symmetrize it, like the original distribution can't be 0, but the symmetrized version can always be 0. And that's sort of essential. So I don't know how to eliminate that. But this is a really interesting conjecture. Yeah, to, I guess, an intermediate question is, can we at least prove that there exist super exponentially many permanents of plus minus 1 matrices? So it might be that the easiest way to prove this is to actually prove this, but this is, in principle, a weaker question. So I should say that this, even for the determinant, so this is probably also true for, well, for the determinant, this was proved just a couple of weeks ago by Shitov. It's something people have been thinking about for a long time, but it took some quite ingenious ideas to prove it, even for the determinant. And so this is probably a hard question. The other question, as I sort of mentioned, is what about...
Wait, sorry, who proved the determinant version?
Determinant version by by Yaroslav Shitov. Yeah, it's not that easy of a paper to find. It's not on the archive. It's on ResearchGate only. But why? I don't know.
Did you check it?
People have checked it. I have examined it for reasonableness. Yeah. So it's a very explicit construction that sort of, it's a way to take your favorite integer and write it as the permanent of some plus minus one, as the determinant of some plus minus one matrix. Yeah, so that's exciting progress. It doesn't look like Shitov's proof works for the permanent, but
You're trying to prove that for any matrix you have that many. No.
so
no,
among all
no,
the
no.
plus minus one matrices,
Oh yeah, right.
really
right,
this is n by n.
Right, right.
Among all the n by n plus minus one matrices, there's more than exponentially
I
many.
see. So by
different-
explicit construction, you mean
So yeah, right. You have the
Construction.
opportunity to do an explicit construction here, whereas you don't for that. But of course, if you could do that, it would imply this. Right, and you could also ask this for 0-1 matrices, and I think that's also open. Yeah. So the Beraldi-Newman theorem is that you can get every integer between 0 and 2 to the n as the permanent of some 0-1 matrix. But presumably the true answer there is also super exponential. Okay, and the other question is, what about symmetric? Random matrices. Because all the stuff that I told you at the start about the singularity problem, all that stuff has a counterpart, well, most of it has a counterpart in the symmetric world. It's generally much harder because the rows aren't independent in a symmetric random matrix. And I think it would be interesting to try and extend this stuff to the permanent. So what is missing is, so for the Tao Vu approach, with Lisa Sauermann, we managed to extend that to the symmetric setting. That's kind of robust, thinking about how permanents grow as you expose more of the matrix. But this recursive approach where you get the boost, well, you need the boost to come from somewhere, and I don't know a way to get the boost in the context of random symmetric matrices. So it seems like some kind of new idea is required for that. But that's that I think would be interesting. So that's all I had to say.
any questions?
In the result by Rasprov that you mentioned during the talk, it was also about the number of.
Yeah, so it was a super polynomial bound for this
I
thing.
see.
Yeah, so e to the square root, e to the square root n or something? I can't remember, but some super polynomial bound.
And it was for the permanent.
It was for permanence, yes. It was by some explicit construction. It did some Diophantine geometry to count in some analytic number theory-ish ways some things. I think I haven't looked at the paper in that much detail.
If you make a skew symmetric matrices, then is it are there some known thing?
Probably it's a similar level of difficulty as symmetric matrices, unless there's some. So there's some miracles that happen with permanence. For example, I think when n is a power of 2, it's actually impossible for the permanent to be 0, and there's some similar miracles, but they're very distribution dependent, and so robust things. I don't think that would be any easier than the symmetric case.
Okay, well, in here, the number of possible values of entries of AN is 2. My question is, if we generalize this problem by increasing the number of possible values of entries of AN, then is there any similar result?
Yeah, that's very interesting. So of course, if I increase the number of variables, in some sense it makes the problem easier, because really all I require for our main result is that the entry distribution has some anti-concentration. So anything with more than 2 values in the support would be like that, so I get an exponential bound. Of course, you could start to ask for a bound that depends in the right way on the anticoncentration. So if you take an enormous number of entries of possibilities for each entry, like in a way that depends on n, then perhaps you should start to get better than exponential bounds. So our approach does give something, probably not the optimal thing for this type of setting. I think that's really interesting to investigate that sort of direction. And also the opposite direction, where instead of making the entries more anticoncentrated, you make them less anticoncentrated and ask, what is the, like, for example, the usual setting in the determinant case is to consider sparse random matrices, where the entries are almost always 0, but with some small probability they're 1, say. The techniques there are quite mature, but for permanence, I don't think we really have anything.
Any other questions? So if not, let's thank the speaker again. Okay, so who wants to join the? Oh, okay. Are we off the record?